Here's an introduction to linear regression. Alright, chapter 7, the introduction worksheet. Look at me. I scanned it and I sent it to email and I uploaded it to here and it's ugly. I ain't gonna lie to you. This is not looking great, but it's later at night and we're gonna go with it. And yeah, things keep moving around, but we're fine. What I did was, these are distances that a plane flew and then the airfare that it cost for the flight. So distances on the x-axis, airfare on the y. So we have a scatter plot here, and you can see it's kind of linear, but there's a lot of spread to it. Well, what we can do, you can see the graph keep shifting every time, but look, we can come with this line of best fit. We can draw it, and we can use it to estimate, hey, if you go like 1,000 miles, how much would the airfare cost? Looks like maybe $350 or so. But that line can help us to predict in the future based on the data that we've already collected. So that's again what we can do. We can say, well, you know what? Let's say we want to go to New Orleans and we want to know the average price that we'd have to pay. Maybe we're going down there and we're going to cage alligators. So it's like, hey, we're Cajun, let's go to New Orleans. So that's where we're headed. But what happens now is this. That point right there was the the distance and the airfare to New Orleans. And you can see that this line of best fit is not the greatest predictor. Because that one time that we did fly to New Orleans, we traveled 1,071 miles and the airfare was $438. But if you follow our line of best fit, it would have predicted that a plane ride of 1,071 miles would cost about $350. So there is some error. There's an error between what we observed and what we predicted. So that difference, which in this case you can see is $88, we call that a residual. So we're going to be doing y minus y hat. That's going to give us our error amount or our residual. And in this case, it's $88. Our observed flight cost was $88 above what we predicted. Now, some of these other observed flights were below. They cost less than what we would have predicted, so they also have an error term to them. But when the observed y is smaller than the predicted y, and you subtract them, you get a negative residual. So this might be like negative $62 or something like that. Well, if you added up all the residuals, they'd all add up to 0 because it's a balancing line. So just like we did with standard deviation, we'll square these residuals to get rid of the negatives and add them all up. So what's going to happen is we're going to find a least squares regression line where we add up the difference between the observed y values, in this case the airfares, minus what was predicted for the airfares. We'll square those residuals, we'll add them up, and we'll see what the sum of the squares of those residuals would be. So we're going to say, oh, here's an error amount, here's an error amount. These are all error amounts. They're these guys right in here. They're residuals or error amounts. We're going to square them to make them all positive, and we're going to add them up. And then what happens is we could say, well, you know what, the green line, if we look at that as our predictor for the y's, and we took all the observed y's minus those predicted y's, squared them and added them up, maybe we get a sum of squares of the error terms being about 45,000. But then somebody says, but I like this red line better. Well, let's see if the red line is better. No, there's too many points down here that are too far away. There's too much of a residual. There's too much error down here for that line, big error here. When you square them, you're going to get too much. So for that line, the red line, we're going to end up with the sum of the squares of the error terms, the sum of squares of residuals, being 67,000. So what makes a line a least squares regression line is when you sum up all the squares of the error terms and it gives you the least possible sum. So we're going to call these least squares regression line, and it's that the sum of the squares of the error amounts, these guys here, is minimized. So that's what we call an LSR line, or a least squares regression line. Now we're going to be using the calculator in this next video to show how we can find the least squares regression line, and we're going to get used to calling it y hat. The predicted y is going to be the y-intercept plus the slope times the x's and in our case it's airfare equals y-intercept plus the slope times the miles traveled. That's how we'll predict what the airfare should be. So if we looked at this, we'd say, well, you know what, our prediction line might do something like this, and so the y-intercept might be at about 260. So we'd say, hey, our prediction line is y hat equals 260 plus, and then every time we go 1,000 miles over, it's going to go up $100. So the slope might be 0.1x, meaning for every additional mile we travel, the price of the ticket, the airfare goes up by 10 cents, 1/10 of a dollar. So if that were the case, we could plug in $100 for X right here. I'm sorry, 1,000. We'd type in 1,000 miles for the X, I should say. So we'd replace this with 1,000. We'd multiply by that by 0.1, giving us 100. So this is really sloppy, but we're okay. So the predicted airfare would be 260 plus 100. Maybe we would predict that for a travel of 1,000 miles, the predicted airfare would be $360. So our regression line is going to predict for us what that should be. Now we can see that we're off by a bit in a lot of cases, so we take it all with a grain of salt, but that's the basic idea behind how we're going to predict it. So let's say we had airline A and we did a scatter plot, a random sample of a bunch of flights with them, versus airline B, we had a random sample of distances and airfare for all these different flights. There's more spread here. There's more variance. So maybe on this airline, we might predict that a 1,000-mile flight would cost $360, but we would not expect that for any one actual flight we took, that would be real accurate. Oh, I'm sorry. We would predict $380, my bad, on this one. But we wouldn't expect that to be terribly accurate because there's a lot of spread. But over here, when we say, well, you know what, for 1,000 miles, we're predicting an airfare, this one's the 360, sorry, predicting an airfare of 360, but because in our sample, all the airfares were holding really close to that prediction line, we're pretty confident that this is a very accurate estimate of what the flight would cost. So this is a basic idea, basic overview of lines of best fit, but now in the AP Stat world, statistics realm, we call it the least squares regression line. It is a prediction line. We are going to predict whatever the y variable is by figuring out the least squares regression line with its slope and its y-intercept, and be able to put in all our various x values, in our case the miles for the trip, and we would predict what the airfare is. We're going to use the calculator to do it. We don't want to go back to the doing things by hand on a graph like we did initially. But there it is. That's an intro to linear regression.